So today is the exam review class. We probably will have 4 calculation problems. I haven't made exam yet. I will do it tonight. So we probably will have 4 calculation problems. Those calculation problems will be a similar level of our homework, but it doesn't mean that it's the same as the homework. There's some variation to test if you truly understand or just follow the steps. If you just like without understanding, just following the steps, there's high chance you may make mistakes. And of course, it's also similar to our example problem in class, but sometimes the example problem in class, especially the first example problem, is like very straightforward application of our theory. So that probably like too easy for exam, but you know what I mean. So make sure that you understand all the basic concept. You know how to calculate, how to solve all the example problem in class. We showed in class, solved by yourself. You know how to solve the homework problem by yourself. And also this is normally for the lecture type of class. These 5 points, ask you for feedback and suggestion questions. I do this for all lecture type of class, like the mechanics materials, aerospace structure, and FEA. For design class, well, I don't do a lot of the teaching, so I don't ask this kind of question, but for lecture type of class, I always do this in exam 1. So this is basically, I know there's a like cost evaluation at the very end of semester, and you can submit your feedback suggestion how to improve. But I want to say that I can benefit from them by knowing how to improve my teaching, but it's only benefit for the students in the future semester, not you guys. So if you want to make your experience here better for the rest 2 months, it's better that you tell me now what I can change to make your learning experience better for the rest of the semester, not just like leave at the end of the semester. Then, I mean, you guys really cannot benefit from all those suggestions and feedbacks. So, and also these 5 points is 5 out of 100. It's not 5 out of 105. So this is not a bonus part. You have to do it. So this is a 5-point question, and the rest, 95 points will be 4 calculation problems. So we start from the actual FEA part, the mathematical preliminaries. I will not ask like how to calculate inverse of the matrix, how to calculate a determinant of a three-vector matrix, or how to calculate eigenvalues, or matrix vector operation, anything like that, because I consider that's really not the really like FEA content. But you do need to know how to do the calculation to solve our FEA problem. You don't want to get stuck, because let's say the first step is solve unknown graphite, and the second step in the calculate reaction force, calculate stress, calculate anything that, if you don't know how to do, let's say, matrix vector operation, you're gonna stuck somewhere, and you definitely don't want to torture yourself during the exam because of that. So make sure that the first 102 lecture about the mathematical preliminaries, make sure you know how to do all those calculations by yourself. And start from the spring element. Actually, let's answer one quick question. The most commonly asked question in the last class. Let's focus on that one first, because I guess a lot of students get confused on that one, and then we can start from one by one. So at the end of the last class, many students asked me like, okay, Dr. Kim showed how to plug this one into the big matrix equation. So for the reaction force at node 1, you have this one times this one equal to this one, right? Reaction for node 1 in the y direction, you have this one times this one equal to reaction force at node 1 in the y direction. And then you have this one, r equals square root of component in the x direction square plus component in the y direction square, and equal to the reaction for node 1. It's completely correct, and it's our standard procedure. So it's perfectly fine. You use this method in your exam. But what I mean in the last class, that to save some time, you can actually, based on our understanding of the reaction force and external applied force and nodal force, and we can have this one directly. So basically, let's say if you have this kind of problem, let's use his example here to explain to you guys. So let's say In the previous step, you already have the element force in element 1, element force in element 2. Now, you compare this one and this one. You know what I mean? You can skip all this part of calculation. But I'm not simply saying that it's always the same. We do need to understand. Now let me show you how to understand this one. So first, let's check his solution. The component, there's a negative sign, there's a positive sign. In the x direction, it's negative sign, and in the y direction, it's positive sign. And we talk about the reaction force is one type of external type force. The sign always follow coordinates. So we know that it basically means that y component is in this direction. X component is in this direction. And the square root of something is always positive, but the component-wise, you know the direction, right? So let's say this is a reaction force is in this direction. Based on his calculation, makes sense or not? Don't get confused like, okay, this is positive value. Well, I can in different quadrants, it's always a positive value because this is mathematical square root is always positive value. But based on the sign here and here, we know what is the direction because one is negative x and positive y. So negative x, positive y. So we know the reaction force is in this direction. And magnitude is square root of that one. And also, let's forget about FEA. We know that it makes sense because if you have a structure like this, if I force, I'll put to this side without any calculation, without learning FEA, based on what you learn from statics, not even mechanics materials, based on what you learn from statics, you would expect that the reaction force direction should be in this direction. Makes sense or not? Without any calculation. So again, first method makes sense. The second method, let's say let's assume that, well, not based on his calculation, since it's from 1 to 3. So our node order, let's put in here. For element 1, we have node order from 1 to 3, right? So basically, node 1 is the first node, node 2 the second node. And as I said in the last class, if it's a second node of the element, element force or internal force always have the same sign of the second node, but in first node we need to add a negative sign. So here we have R1 should be equal to, since it's the first node, we add negative sign of element and equal to negative. Sorry, his F was square root 2, right? And what does this one mean? Yes, it's a negative sign. Wait a second. It's a negative sign. So basically, because our local x coordinates is defined from 1 to 3, and now I have a negative sign, it basically means that it's opposite of our local x direction. So it means that this is a magnitude, this is the direction of our reaction force. This is local x, this is reaction force. Makes sense or not? It's the same thing. It's the same thing. So if you guys like still confused about the basic concept, like y is always the same as the second node, opposite of the first node, let me show you our lecture at the very beginning of the semester. This part. So basically, I said, this is the first lecture of the FEA content. I said, if you want to generate tension in our structure, what do you need to do? You need to apply force in this way. So basically, at the first node, node I is in the negative x direction. At the second node, node J, it should be in positive x direction. Makes sense or not? So tension, internal force positive. Node I, nodal force at node I, first node, negative. Nodal force at node J, positive. And if we want to generate compression, what do we need to do? Apply force in this way, right? Now, if you check the two nodes, nodal force at two nodes, well, compression, of course, by the sign convention of internal force is always negative, and our nodal force applied at node I should be in the positive x direction, and nodal force applied at node J should always be in the negative x direction. So now let's check, focus on this one. Now you can see, of course, everything is in equilibrium. So in terms of magnitude, internal force or element force, magnitude same as nodal force node I, nodal force node J, force equilibrium. For the sign, now you check this one, element force or internal force always has same sign of the nodal force at node J, and negative of nodal force at node I. Makes sense or not? Now back to the example problem. Based on our definition, we define node 1 to node 3. So 1 is the first node, which is node I in that conceptual part. Node 3, the second node, node J, right? So reaction for the boundary condition is at first node. That's why we added the negative sign. And of course, let's say node order or local x direction or any coordinate system is just convenient for your calculation. We can really define it any way you want. Let's expand it a little bit. Let's assume that what if I define element 1 is from node 3 to node 1 to see if you get the same results. So if we define from node 3 to node 1, do you agree with me that element force will be the same? Right? Element force is internal force. Tension, compression is always have the sign convention doesn't change. So if it's tension, no matter how I define node order, so this one is still the positive f over square root 2. So now if I define this way, basically it means that our boundary condition is applied at second node. So the nodal force should be the same sign as our element force. So let's say in that situation, I use a different color. R1 should be equal to P1. Because based on new node order definition, this is a second node. Second node should always be the same sign as the element force. And now it should be F over square root 2. And now let's see what it means. Well, magnitude is always the same. And now it means that node 3 to node 1, this is our local x direction. And the positive value means it's in our positive local x direction. So it also means the reaction force is in this direction. Make sense or not? So this is like some students that really hate if there's too much math, too much calculation, and some students even put in the cost evaluation that said our department should remove the FEA from mechanical engineering program because it's too much math. I want to say that FEA is not just math. It's truly about your understanding about the solid mechanics. And like the thing like software ANSYS, Abacus is just some advanced software to alleviate you to do really the calculation by yourself. But the whole thing itself is about your understanding. So if you truly understand what the reaction force means, what the internal force, external applied force mean, what the element force mean, what the relation between them, actually this class is kind of easy, right? So here, by using your understanding, you can skip all this calculation part and just simply say, okay, either you do it this way or you do it this way. Save you some time. Any question? Yes. And also it depends on like which node is really the boundary condition. Yes. Correct. So it based on our understanding from the first lecture of our FEA. Yes. Any other question? But of course, in the exam, any method you want to use, that's fine. But if you want to use, let's say this one, make sure you have very clear definition of your node order at the beginning of the solution. Otherwise, TA doesn't know what your positive and negative means, right? And there's no way we can grade. If you want to use this one, you need to have a connective table to define for each element what is first node, second node. Yeah. So this is a question asked frequently after last class. Or any other question you guys wanted me to explain first? Okay, so let's do it one by one. Yeah. Displacement matter? Like if you want. Great question. What do you think? Yes, but also I see the structural benefits. It didn't really apply. Let's forget about FE8. Do you think it should affect or not affect? Doesn't, right? Again, the node order does not affect the displacement results, because let's say in 1D situation, we put this one as positive x. And if your displacement is positive 1, it means in the positive x direction for 1 meter. If negative 1, it means in the negative x direction for 1 meter. And the displacement is only for that specific node. It does not depend on which element. Let's say, well, this node 3 can connect with node element 4, element 3, element 5. But we never really say like, oh, displacement of element 3 and node 3, element 4 and node 3, or element 5 and node 3. Displacement is only about the node. It does not depend on which element. So no matter how many elements connect to, displacement, if I get positive 1, it means in the positive x direction for 1 meter, if let's say meter as unit. And also in the global, in the 2D space, we set the equation and everything, let's say, is always in the global xy coordinates. We always have this one as positive x and upward and positive y. So whatever you solved is only in the global xy coordinates. It does not depend on like I define you 1 to 3, 3 to 1. That is the local x direction. In the end, we convert in the theory part. You can check. I didn't put a complete like derivation, the theory, everything here. But if you check the detailed derivation, like convert from 1D to 2D, you will see that it really, in the end, is solving the displacement degree freedom in the global xy coordinates. And once as long as we have the global coordinates, it doesn't really matter, right? And for thermal, of course, it's the same. Yeah. Any other question? Global, you don't define. We always, well, normally if it's 1D situation, we put this one as local x. Normally, if it's 2D situation, we put this one as global x. The purpose of a global x coordinate or xy coordinate is that, okay, let's say we have a truss system and each bar has its own local, right? And it's more like different bar in a truss system, they are using different language. And if you really want to assemble them in a big matrix and solve them, we need to make sure they are speaking the same language. And the global coordinates is make sure that, okay, now every element in our truss system, no matter what angle it is in the 2D space, it always has a global, the same coordinates. So we don't change like 100 students here, we have 100 global, then what's the point, right? So we normally consider this is like the one language we speak, yes. So basically like 100 students solve 100 solution, you should have the same of the UI, UJ, VI, VJ. Yeah. Thank you for the question. What change? Temperature change. Yeah. 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 Especially if they like, because I saw it at the workplace, if you change from the nodes, like how the argument is defined, like 1 to 2 to 2 to 1. Yeah. Then yes, yes. So let me start from the basic first. This is the basic equation we have. Make sense? And you can have different, let's say, different people have different I and J definition, but it doesn't matter. So let's say if you have, let's say the example I just showed, 1, 2, 3, and then 1, 1, 3, 3, right? And then you have from 1 to 3, you have the corresponding phi, you have a corresponding L and M. You put it here. And also this 1, 1, 3, 3. If you define from 3 to 1, they become 3, 3, 1, 1, 3, 3, 1, 1. And for the 3 to 1, you have different phi, and you have different L and M. This part is the same. I guess your question specifically related to our homework. I can show you how we solve the. There's some delay here. Yeah, this one, right? Yes. Okay. As long as you make it consistent, the final answer should be the same. Once you have, let's say you have your own definition of I and J, so you have your own phi and L and M. And then in your equation, the I and J is based on your definition. Everything is, as long as you make it consistent, your solution should be correct. That's what I mean. Yeah. It doesn't really change. It doesn't really matter like which is the first node, which is the second node. So let's focus on this example problem. This is my definition of a node order. You can define it any way you want. So basically, 1 to 4, 4 to 2, and 4 to 3. This is my node order definition, and this is the corresponding angle phi and L, sine and cosine phi. So for element 1, again, if I'm defining from 1 to 4, then 1, 1, 4, 4. If you define from 4, 4, 1, 1, that's fine. And this is external applied force. Obviously, we don't have external applied force. But doesn't mean this one is 0. This is the nodal force for that element. You add 3 of them together, there's no external applied force. So this is corresponding L, negative M, L, M, M. For element 1, for element 2, since I define from 4 to 2, now it's 4, 4, 2, 2. And same thing here, negative L, negative M, L, and M. This is for element 3, defined from 4 to 3. And this is a thermal term. At assemble this 3 matrix, only if all the components related to node 4, because we know that the other node doesn't really matter because it's boundary condition. We need to know that this one plus this one plus this one equal to external applied force applied at node 4 in the x direction and in the y direction. And since we don't have, add these 3 terms, since we don't have force applied at node 4, so those 2 components in that vector should be 0, 0. Make sense or not? I skip that part. There should be a actual vector that is corresponding to this one plus this one plus this one. Should be 0, 0. And so now we have 2 by 2, and these 3 components come from here plus this one plus this one. We have. Any question? If you have any question, ask me. Does this make sense or not? Sorry, who has a question? Element force. This was the equation provided in the class, right? And we solve for the U4, V4, and this is the only non-zero displacement in our whole structure. U1, V1, U2, V2, U3, V3, they are 0. So based on your definition, what is node J, what is node I for each element? You have element force, element force, element force for 3 elements. And of course, in the example problem I did in class, we only have the first element has temperature change, and the second element third element, there's no temperature, so we didn't have these two terms. But here we have temperature change for all three elements, so don't forget this part.
So, please go a little bit.
Where?
Yeah, okay. So the force that node 4 is the same for everyone of 3 and of 3, which is 0.
Sorry.
The force at node 4.
No force applied means 0.
Yeah, 0.
Yes.
It's the same for everyone, element 3 and element 3. When you make the matrix, the 3 matrix.
Great question. What do you think? Great question. So again, this is not a FEA problem. This mechanics materials and statics problem. So when I said there's no force, if you have a question, you can ask me. There's no force applied node 4. It means that the force applied at node 4 to element 1 plus element 2 plus element 3, the 3 combined equal to 0. But if you just imagine, let's say all 3 has expansion, and of course, all 3 want to expand the same, since the same temperature increase, so they want to expand the same elongation. But since the point is symmetric, they need to stay somehow in this way. So there is like, how should I say? The actual elongation in this element should be smaller than free expansion, right? So we cannot say that the force applied by node 4 to element 1 is 0. It's not 0. So also the force applied by node 4 to element 2 is not 0. Force applied by node 4 to element 3 is not 0. It's just like if you have, so basically what I mean that mathematically, this one is not 0. This one is not 0. This one is not 0. But if I add these 3 terms together, it should be equal to the externally applied force at node 4. And that one should be 0. Yeah. But since they are constraining each other when they want to expand, it's different from free expansion. Let's say if I do not connect these 3 points, then you can check out the class, like the displacement generated from the elongation generated from free expansion and the elongation we generate from here. Since we have the U4, we will calculate it. You can compare, the elongation is not different. So basically, because of constraint of each other, they will generate some force, internal force. Yes. You're welcome. Thank you for the question. Any other question? Yes. Yes, I posted it, right? Yeah, yes, I posted it. And also there was one question before the class. The students said we need this one. I will add this one tonight, and I will upload that equation sheet on Canvas. So I will add this one. So basically, I write as L and M. Yes. Transformation matrix. Any other question? Let's see how much time do we have. We have 20 minutes. Where was I? So for let's back here. The most of the real life situation is that you have the K matrix, because if you know your structure, you know the K matrix, you know boundary condition, you know the external applied force, you solve the analytical freedom, right? That's commonly what we may experience as structure engineer. Or this one, the homework I think is that if we hold one element, oh, here. If we keep some a specific element from moving, how to calculate what force should be applied. So it's basically the same equation we use in different direction. So let's say we have KQ equal to F. If we know the K, we know the F, how to calculate Q. That is most question how we solve those. But of course, mathematically, if we know the K, if we know the Q, how to calculate F, right? So basically, it's the same equation we calculate in different direction. So just hope you understand that it may say in different ways, but it's the same thing. There's a question. So this is for spring element, and for I want to talk about this one because I also got many questions about this one. I talked about the displacement field at the beginning of last class. Let's talk about the stress. Stress, yes. I didn't really do example problem like calculate stress in class, but it's simply because this part like calculate stress is simple enough. But I want to tell you that for the stress, 2.5, so it's midpoint of this one. Some students like really focus on 2.5, how to use a 2.5. It really doesn't matter. I can say 2.1, 2.3, 2.4, right? Because we know that based on the first topic of mechanics materials, we know that for tension compression, for this section, this section, this section, for each section, they have the same stress, no matter which point in that section. So of course, I put this 2.5, but it doesn't matter. It does not affect your calculation of the stress. If I use 2.1, 2.3, you do not always think about how to use 2.5 in your equation. It doesn't really work in that way. And also, I want to say that for calculating the stress, actually we can do in different directions. So let's say the first step, you probably calculate the nodal displacement. So based on nodal displacement, you can calculate element force. Right? Let's say you have the force, you have the displacement at node 3. You have displacement at node 4 equal to 0. So basically, you can calculate element force in this third element. And stress is equal to element force divided by cross-section area. You get a stress. But of course, again, based on mechanics materials, we know that stress can also calculate from the strain. So basically, what you need to do is that, okay, I have the displacement here. I have the displacement here equal to 0. I have the original length equal to 1. So elongation here is the contraction, of course, is negative value. Delta in this section times Young's modulus equal to stress. Both of them are correct. So again, this is like how to calculate stress and what the 2.5 means. Don't get confused like how to use 2.5 in your equation. You don't really need this 2.5, doesn't really matter. And another thing is that for this one, be very careful, is from the global X to local X counterclockwise. So in the lecture, let me show you. I asked Dr. Kim this morning, like, what it's a BW means, and he said it's between. So what he wrote here is the angle between the global X and local X. I think he explained in the class that it should be counterclockwise, but somehow if we say between, let's put it this way. Let's use his example. If you really say between the global X and local X, I mean, you don't really need to put negative sign. Makes sense. This could be, I mean, I can do in this way, this is 45. I can do in this way, it's still 45, right? There's really no negative sign. And this angle, if I say angle between the global X and local X, you don't really need to put negative. So just make sure you truly understand what it means. Is the exact definition, because we did all our derivation based on this definition. It should be from global X to local X counterclockwise. That's why we need to put a negative sign if we define in this way, right? So make sure you truly understand what this angle phi means. If you mess up this part, the phi is wrong, the L and M is wrong, and all your K matrix solution, they're all wrong. Any question? That's why I intentionally put the very clear definition here. The phi angle should be global x to local x counterclockwise. It's not angle between. And as I said, I will add this one to our equation sheet. And I will this one. Well, I have the element force calculation, but that one is with the temperature change. Of course, if you put temperature change equal to 0, you get this equation, right? So it's the same thing. I don't think I need to write like actual equation for the element force without temperature change. So these are the two homework problems. Any question for these two homework problems? There's no temperature change in this problem. Which problem? First one, what? Oh.
Yeah.
Which one?
I think it just says that alpha is the coefficient from
We are not finding coefficient. Coefficient of thermal expansion is given information. You just use alpha for calculation. I'm not gonna ask you like how to calculate coefficient of thermal expansion alpha. Well, I probably should move this one to the beginning of the problem statement then. Yes. Any other question? Let's back to homework 3 first. Any question about the homework 3? Again, this one is like displacement given calculated force. So same thing, right? We have K times Q equal to F. And now Q is given calculate F. And be very careful for the force. Calculating the applied force. This force F here is the external applied force. Externally applied force follow the sign, follow the coordinates. So make sure you have the same correct sign for the force applied. And for this one, again, it's not really like understanding problem mistake or attractive solution. The common mistake is really you need to know that the L of this one, L of this one, L of this one, they're not the same. This is not really just need to be careful in your calculation. There's nothing related to that truly understanding of our basic concept of FEA. Is you just need to know that they're not all equal to L. The information given here, this is L, so this one and this one, they're not L. And this is the equation for situation when there's a temperature change. And element force, this equation is provided and posted. Example problem I did in class is when there's one temperature change for only one element, and the homework is what if we have temperature change for all 3 elements, calculate same thing. Coefficient thermal expansion alpha is giving information, is not asking to calculate the coefficient of thermal expansion. And for this one, solving nodal displacement, always the first step. If I don't ask you solving nodal displacement, you still need to solve nodal displacement before you calculate element force, reaction force. What else? When put the F in the force vector, make sure that this is the force in the negative x direction, so you need to put a correct sign. Sorry. You need to define your node order.
Yeah.
That's fine. That's fine. That's fine. No. But you need to make it very clear that what is the first node, second node, because first node, second node have different sign, and so TI knows if your calculation is correct or not, or it's caused by if there's any error. Yeah. Correct. You're correct. So no matter how I define node order, if the tension for element force is always positive. Its compression for element force is always negative. So no matter you are different, have different node order. And I just use this example to show you that for this one, I can use 3 different methods. The first method is this one. We know that, okay, this is the reaction force direction. And I can also use the one I talked about in class based on the relation between the nodal force and reaction force and the internal force. And for this one, I get negative value, but still it means reaction force in this direction. Or I can define the node order in a different way. Let's say I define in this way. And now I have reaction force equal to element force, because now it's the second node based on node order definition. Now I get a positive value, but still it means the same thing. It's still the reaction force in this way. So in the end, the reaction force magnitude direction does not depend on how you define your node order. But you need to make it clear in your solution at the very beginning, what is the node order definition? So we know what the positive negative means. Yeah. Any other question? Let's see. Let me show you the solution for last one. For this one, that's what I said in the class, that to save you some time. Before I cross out the components is a standard solution, and you can see that 4x4, 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 8x8, and delete the corresponding row and column, you get a 2x2. That's what I mean, that you don't really need to write a complete matrix equation. And I'm sure that if you write like this one, this one, this one, and it's complete 8x8, I don't know how much time it takes, but you probably cannot solve 4 problems in 2 hours. That's what I mean. Really focus on, as engineer, we need to know that what are the necessary information to get what I want, and only focus on those informations. Don't waste your time on the things that we don't really need. And the standard solution also use like the big matrix equation. And if you use big matrix equation, again, you don't really need the whole this part, right? Because we know that these 6 components are 0. So if if you're familiar with matrix vector operation, you know that this one really doesn't matter because they are 0. So let's say if you want to use a standard procedure, calculate reaction force, reaction force in the x direction and the one x, the one in y. So basically, they are corresponding to this component. You only need complete this column and this column, but you don't need here information here. Doesn't matter, right? So this is a standard procedure, and of course, if you use what I said in class based on our understanding of nodal force, element force, reaction force, you can skip all the calculation and write those 2 columns in the matrix. The last question. Again, collective table. This is for element 1 with temperature change. Element 2, there's no temperature change. Solving for the unknown element force, reaction force. And again, this here, reaction force, I use the method I talked about in class. Any question about the exam? If no question, we're done for the class today. Thank you for coming and have a great day. I will be in the office hour in MAC 106.
Thank you.
You're welcome.